Hello, I'm Isaac. This is my lab for circuits. The purpose of this lab was to utilize principles of current and energy conservation through criteria set by the loop rule and the definition of a steady-state circuit. We also wanted to predict and examine the behaviors of RC circuits with ohmic resistors and capacitors. We utilized multimeters to calculate those values related to the circuit. The brief results of our lab were we found currents 1 and 2 to be approximately 0.0172 amps, and that the predictions of our values of currents and voltage closely resembled the calculated values from the multimeters. The fundamental models and principles we'll be utilizing in this lab are Kirchhoff's loop rule with the potential difference of round trips equaling 0, the node rule, steady-state circuits, the conservation of energy and charge, Ohm's law shown by these three equations on the right, and resistor-capacitor circuits, also known as RC circuits, shown in this diagram. The assumptions we made in this lab were that we assumed that the resistance of the ammeter is negligible and that the resistance of the wire is also negligible. For this experiment, we first created a circuit consisting of two ammeters set to read positive values, two 1.5 voltage batteries, and two resistors. The predicted current that we had for current 1 and 2 before we started this experiment was 0.02041 amps. However, after this experiment, we found an actual value of our currents to be 0.0172 amps. Now, if we actually reverse one of the connections to the ammeters, the value for our current will be the same, however, the sign will change. So the value with a reversed ammeter would be negative 0.0172 amps. In our second part of our experiment, we replaced one ammeter with a voltmeter by simply flipping a switch. Well, from our readings, we found that the ammeter read a value of 0 volts, while the voltmeter read a value of 3.07 volts. This implies that the voltmeter has a high resistance value, which impedes current to a negligible amount, proven by the ammeter reading 0 volts. In the third part of our experiment, we removed the voltmeter and closed the circuit with an additional wire. By doing this, we were able to calculate the potential differences in each point of our wire. From A to B, we found a potential difference of 2.66 volts. From C to D, we found a potential difference of negative 0.87 volts. And from E to F, we found a potential difference of negative 1.79 volts. The rest of the points had volts readings of 0. And if you notice, if you add all three values, they will add up to 0, proving the round-trip theorem. And the current that was flowing through this part was 0.0172 amps, which was agreeing with our previous value. Here's our graph of potential showing the negative values of the potential difference in purple. And notice how the beginning of the graph and the end of the graph end at 0, once again proving the round-trip theorem. In our final part of our experiment, we constructed an RC circuit consisting of two light bulbs, one being 10 ohms and one being 20 ohms, one 9-volt battery, and one 200 millifarad capacitor. When we charged the capacitor and connected it to the light bulb, we found that the capacitor slowly discharges, gradually decreasing the amount of current that flows through the light bulb. So initially we saw a bright light being produced in the light bulb, but then that light slowly dissipated and grew dimmer. Here are my calculations for the slope value, which I found to be approximately 0.167. From our experiment, we have to acknowledge the sources of error that could have arose. Possible sources of error may stem from human error when reading and transcripting values from the ammeter to the voltmeter. So, for example, we could have made a mistake while reading a value and then writing it down. Another possible mistake was that human error in the initial circuit setup. For example, we may have misplaced a wire, or we may have accidentally set up a wire. And a third possible source of error were worn out or previously used batteries, which result in inconsistent readings of voltage. Now, what if I was doing this lab online, where I was able to use an ideal simulated ammeter? What would be different about a simulated ammeter, and how would it affected my results? Well, that since an ideal simulated ammeter would have 0 resistance, more current would have been able and allowed to move around our circuits in this experiment, which would greatly alter our values of predicted and measured current. Here's another scenario. What if I was doing this lab virtually and used an ideal battery to charge an ideal capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, if we use an ideal battery to charge an ideal capacitor with no resistor in the circuit, the capacitor would theoretically instantly charge, since there's no resistor in the ideal battery, in the ideal capacitor, or no resistor in the circuit to impede any flow, meaning the capacitor would charge instantly.